So let's kind of go through a hands-on demo, the first one. Okay, so we'll go through the three solutions which we just talked about. We are using LangChain here, and Unstructured is an open source tool from unstructured.io, which is a great way to load up data, separate the tables, images, do good chunking, and so on. So here we have just taken one PDF document. As you can see, this is a popular research paper, layout parser. It has some text, as you can see, and it has some images, some tables. So what I'll show you is you can use relevant document loaders and extract these separately so that you can process it in a better way. So here we download the PDF file, and then we have the unstructured PDF loader wrapper on top of the unstructured library in LangChain. You just specify your document name, mention you want to use a high-resolution extraction strategy, mention that you want to extract the images in the document, extract the tables separately, and you can even specify the chunking strategy here. One of the naive chunking strategies is just chunk based on the number of characters. Here you can even say chunk it based on the major titles, right, the major headings in the document. So the chunking is slightly better. And you can specify chunk size in terms of number of characters. Now, once you do that, you will see that it has extracted certain elements. The composite element is typically text, and tables are, of course, the tables in the document, like this one. So if you look at one of the extracted elements, you have the metadata, of course, and you have the text content. Let's look at it in a slightly better way. You can print it out, and you can see here you have the layout parser, the heading, author names, abstract, and the keywords. So it has extracted the first part of this document. But you can see in the first chunk, we don't have the introduction, so it has not mixed up the introduction with the abstract. So in that way, you can control your chunking based on a section-based chunking using the unstructured library. And you can also extract the tables from the document separately, and then you can create summaries of these tables, store them in a vector database, and enable more efficient retrieval based on asking questions even on the tables. And of course, it also extracts the images. So as you can see here, this is one of the images in the document. And it has identified it quite well and extracted it. So what we can do with the images is we can pass these into vision large language models like GPT-4o, GPT-4 Vision, and we can ask it to give a description of the image. And then we can put that description into the vector database also. That's one of the main ways in which multimodal RAG systems are built. Let's talk about the second one, better prompting to prevent them from hallucinating. So let's look at the model we are using here. So we are using a standard GPT 3.5 large language model using the chat OpenAI interface. And here we have a standard RAG prompt, as you can see here, that you're an assistant for question answering tasks, give an answer to the following question with the context provided. And then you have the question which will be supplied at runtime and the context which, let's say, we have already retrieved from a vector database, just for simplicity. And now let's say our context here is two documents on cricket. One is the World Cup champion, and one is the 2020 champion. But let's say your question is, who is the Euro 2020 champion? Right? So Euro is football, as we know. So now if you ask it, it ends up answering the question. So it's answering the question. Now, this is not really a hallucination. The answer is correct, but it's answering the question from its already trained data, right, on which ChatGPT was trained, the public data from the internet. But let's say you're building a chatbot to serve your enterprise customers. You don't want them to get answers to irrelevant questions. So one way we can constrain the RAG system is you add in some more constraints into the prompt, saying, use the following retrieved context to answer the question. If no context is present, or if you don't know the answer, just say that you don't know. Don't make up the answer unless it is there in the provided context. So if you word your prompts clearly, more than often what you will see is it will not answer the question. So if we modify the prompt now and we ask the same question, it will say, I don't know. Now this is fine, but can we go one step further? Let's say that we don't have the answer in the context. We don't have the answer in a vector database also, supporting documents. Can we build an agentic RAG system where we can go and search the web automatically and get the information, answer the question? Now, what is an agent really? In simple terms, agent is basically a combination of LLM, your large language model, prompts, and tools. Prompts instruct the LLM to understand which tools to call to solve specific problems. So the LLM will understand based on your prompt that, okay, I don't have this information, I need to call this tool. As long as you tell that, okay, you have these tools at your disposal. But the LLM will not call the tool for you. You have to call the tool yourself. So I'll show you how you can build a agentic RAG system in less than 30 or 40 lines of code. Now, you can use a lot of complex frameworks like LangGraph, AutoGen. If you're building a really complex agentic RAG system, it's a great way to go about it. But if you're building a simple RAG system where, okay, if you don't have the information, go search the web, get it, I don't think you really need these tools because they add a lot of overheads in terms of latency and other things. You can actually code it out completely in Python and do it. So let's see how we will build this. Now, to build the agentic RAG system, one thing we need is a search tool. We have a lot of search tools out there. We are using the Tavily search API. So in Tavily, you just say that, okay, get the top 3 results for your input question and return the text content of the search results. Now, one thing to note here is you can use other tools also. If you want to access Wikipedia, you can query Wikipedia. If you have other databases or online repositories, you can create a tool out of it. All you need to do is import tool, put a decorator here in your function, and call the relevant API. So now, if we have that same question and we call our tool, as you can see, it gets relevant information from the internet search query. So now the idea is, can we put this tool into the LLM so that whenever we ask a question, if the relevant information is there in the vector database, it will answer the question from the vector database. But if the context is not there to answer the question, it will search the web and answer the question. That's the main workflow we are doing here. So the first step is you have your tool. Here we have only one tool. Bind the tool to your large language model. Here we are using GPT-4o Mini, which is a pretty cost-effective model. And then what we do is we improve our prompt now. We say that, okay, you're an assistant for Q&A tasks. Use the context information to answer the question. If no context is present, which means nothing was retrieved, or if you don't know the answer, check and see if you can use the tools available to you to get the answer. And we have the question and the context, which we will supply. So we have improved it now by saying, don't just say you don't know, search using the tools available if you don't have the relevant context to answer the question. And now, if you see here, we have the same context and the same question. So now if we call our chain, you can see that it does not return any response. But it returns a tool call saying it has identified that, okay, I don't have the information in the context to answer the question, but I do have a tool called search web, which we defined earlier. So I can call that with the query to get relevant information. So an LLM is a great reasoning tool which can understand if it does not have relevant information to solve your problem, it can then call relevant tools. But you have to call this tool yourself. That step is still missing. And if you see here, if we ask a question relevant to the context, then it just answers the question. So one check we can put is if the response content is null and a tool call is present, then call the tool, get the information. If there is a response, then just show the response. That means it was able to answer the question based on the context. So this is our agentic RAG code, as you can see, roughly 25 lines. We take the question and the context information. We create a mapping that, okay, if the LLM says I need to search the web, then we need to call the search web tool. Now, initially, we just call the RAG pipeline that, okay, here's the context, here's the question, try to answer the question. Now, if the response.content is non-null, which means like this, then the answer is there. So you just show the answer, and you say that answer is in the retrieved context. But if there is no response.content, like in this case, but a tool call is present, then just call the tool, extract the text content, that becomes your context, and then pass that to your RAG chain with the question. So this is basically where you're calling the Tavily search tool and then answering the question. And worst case scenario, you just say no answer found. So in this case, when you ask T20 champion, it's in the context, So it just answers the question from the context. If you say, okay, who is the Euro 2024 champion, which just happened a few months back, then it is calling the search tool and then answering the question using the retrieved context. So that's how you build the agentic RAG system. This is a very simple agent, by the way, just searching, but very effective, and you can connect your LLM to various tools in the same format, use the exact same code, and you can do a lot of things. Okay, back to the presentation.